So I'll share the slides now.
Yes, madam.
Good afternoon, all of you. Yeah. So okay, so I will be talking on the future of wireless communication. So like we are talking about currently 5G system, and we are looking for technology to evolve 6G system. So why do we need to move to these future technology? What is the need for that? So when we talk about your current cellular band, so that is your 3G, 4G system, when you talk about them. So the problem that we are facing is that cellular industry is basically thriving on ultra high frequency band. Existing 4G band is ultra high frequency band. That is only 1% of entire regularized spectrum when we talk about the entire spectrum that is available. So ultra frequency band is only 1% of that. So what we can do is we can move to higher frequency that is in the range of 300 megahertz to 3 gigahertz, that is commonly called as millimeter wave communication. And the terahertz band has been considered for mobile communication, as wavelength in this range are. So now when we talk about these bands, there are certain, since this is high frequency band, so automatically when frequency is high, your wavelength will be small and will have disadvantages based on that. Also, it offers some advantage plus disadvantages are there. So at high frequency, your antenna size will be extremely small because wavelength is very small. So antennas are short enough to allow small antenna that can fit in handset. So you can even fit multiple antenna on handsets. So that is the advantage that it offers. Disadvantage is long enough to bend around or penetrate obstacles. So wavelength is very small. So they penetrate will not penetrate through the obstacle, and they'll bend around the obstacle. So attenuation is very high at very high frequency when we talk of such as buildings and foliage. So around these obstacles, it will not be able to penetrate. So signal transmitted at low power, supported by handheld device, can travel reliably up to. So when we know that when device is mobile, you have a limitation of power on it. You can support only power up to certain extent. Also, since it is charged by a battery, so or it is supported by a battery, so and battery has limited lifetime. So because of that, you can transmit only with a limited power when we talk about handheld devices. So at signal transmitted at low power supported by handheld device can travel reliably up to several kilometers in about any radio environment. So in any radio environment at low frequency. But when we move to high frequency, it will attenuate faster. So this is this figure shows how we wish to expand. So from 4G to 5G system, these are the factors that has improved. So like when we talk about performance of a system, we monitor all these parameters. We talk about what will be the performance when the mobility of the device will be high. So this indicates basically what we achieved in the 4G system. So this basically the dotted line indicates what we are able to achieve in 4G system. So here mobility in the range of 50 kilometer per hour. Data at very high velocity is challenging because you have more attenuation when because of relative motion between the transmitter and receiver, the challenges will be high. The peak data rate that is achieved or that was targeted in 4G system was 100 megabit per second. When we talk about further 5G system, then the targeted data is 10 gigabit per second. So these are the parameters we are looking to expand here. Then mobile data volume. So we are expecting that, like since many applications have moved to mobile devices like video streaming, video calling, and there are online shopping is there. Then there are many applications which has now moved to mobile device. So mobile data volume the data transmitted over mobile has increased, and the 4G system support this much data over the mobile device. Then end-to-end latency. So delay between the transmission and reception of the data is your latency. So is 25 millisecond in case of, so when you the delay between transmission and reception is 25 millisecond in case of 4G system, and this is the targeted one. So, and in case of 5G system, what is targeted is this to reduce to 5 millisecond. We want improvement in all direction in case of 5G system. Reliability, when we talk about, is 99.99%. So we wish it to improve further. So because there are some applications, because we are monitoring the control applications, even home automation, there are many things which has moved to mobile devices now, or which are wirelessly controlled by wireless devices. So because of that, we require higher reliability over when we communicate data over these wireless devices. So reliability we are targeting for in case of 5G system is 99.999. That is third order decimal. So further improvement in reliability of transmission. Service deployment time. So the time required, we know that in wireless technology, you need to mount antenna. So the deployment time over a new place should be small. So earlier it was 90 days in the 4G system. Now we want that to reduce it further to 90 minutes. Then the 4G system is able to achieve a certain energy efficiency, and we want to increase it further by 10% of current consumption in case of 5G system. We want to basically, because as we are increasing the number of applications that are accommodated by the wireless devices, and there is a constraint on the battery power that is there. So with increase in application, if your battery of the system of wireless device exhausts, then irrespective of whatever features the device offers, it will be of no use beyond certain extent. So we want that the battery consumption expense, right? So you for the same amount of work that you are doing on mobile, your battery consumption reduces. So we want the energy efficiency to increase as we move from one technology to another. Then the number of earlier there used to be one device per person. Now we have 3 to 4 devices which are wireless devices which are used by a single person. You have tablets, then watches there, and there are multiple devices which are wireless devices which are mutually connected and are used by a single person. So which basically requires you to accommodate more number of users. So here, when we move from 4G to 5G system, we require that the number of devices that can be accommodated or that can be connected should increase with the advancement in technology. So here, so these are the parameters we are looking at. So they further improve as we move from 5G to 6G system. So this is actually so this is transition 6G when we look at. So here the speed further, data transmission rate further increases. Latency, we look for extremely low latency, delay between transmission and reception. Extreme reliable communication is required, right? Reliability should further increase from what is achieved in 5G system. Now, in 4G and 3G system, we have seen that we have improved the modulation technique. We moved to higher order modulation. Then we introduced OFDM in order to better modulation. On system level, we work to improve the performance of the system. In order to increase the data rate, we worked on the system level to improve the performance. Like we improved the used OFDM system in order to accommodate more number of carriers. Then we used higher modulation techniques, then better coding schemes. All these things we looked at in the earlier 4G and 3G system. But now, even with that, we are not able to support the increase in data rate that is expected. So that's why we are looking for higher bandwidth, and we are moving to higher frequencies because of that, so that we are able to address the increase in data rate that is required. The advancement, improvement in these features, that is using the different modulation technique, even NOMA is used nowadays. So they improve the capacity up to a certain extent, but that will not be sufficient to address the increasing demands that we are seeing. So we expect extremely massive connectivity and sensing. So we have the idea is to use we are looking for everything to be wirelessly connected. So that also includes connecting multiple sensor nodes that are there, which gives you information regarding the different parameters, like smart cities are incorporated. So there are many features that need to be connected together here. So we are trying to wirelessly connect when we move over from one technology to another. So more and more users will be connected together. Extreme low power consumption and cost reduction. So as application increases, your battery consumption will increase. So you want that for we have battery is a limited resource. So we want energy consumption. In order to extend the battery life, our target is to reduce the power consumption of over the device. Extreme coverage extension we are looking for. So we are targeting to cover larger and larger areas. Extremely high speed and high capacity communication. So high moving devices, because bullet trains are coming in, and then many high speed devices, because communication over high speed devices is challenging. So with the advancement in technology, it should be able to incorporate all these things. So what we are looking for 6G and beyond is it connect the world, provide ubiquitous wireless connectivity among people and devices. So symmetric transmission across all people and devices, accommodate rapidly growing number of intelligent devices and services. So these are the target application of 5G system. That is next generation cellular and Wi-Fi. It should be able to accommodate. We have more data. Earlier, the requirement or the data which was viewed on internet was or moving on internet was very small as compared to the existing existing scenario that we have. So as the time increases, you will have more data on internet, and that will require more bandwidth. So next generation cellular Wi-Fi, it should be able to accommodate. Then smart home spaces. So home automation is one application that you know of. Then multiple sensor to see water consumption at a place, temperature monitoring. So these are different features of smart cities. So that will be wirelessly. Multiple small sensors will be monitored through these wireless devices. Autonomous car. So we are looking for vehicular to vehicular communication. So the car will be able to move freely without the need for driver. Then we have smart cities. Then body area networks. The devices on the body will be connected through internet. Then we have internet on things. So the further new incoming technology will be able to accommodate all these things. Now, with the advancement in technology, there are challenges. The main challenges that we face are on the network level. The challenges are this spectrum is scarce. You do have finite spectrum. So as the number of users increases or the data required by them increases, so since it can support a finite number of users and a finite amount of data rate, so that is challenging. Demanding diverse application. like even if you look for millimeter wave communication and terahertz communication in the very high band, so it has limitations that it can communicate up to a very short distances, around in the range of 100 to 200 meter. So the application, like it will not be able to very much support your high speed moving vehicles. So that has certain limitations are there. So spectrum that can accommodate or that can move freely across to larger distances is very limited. Then we are looking for reliability. So the data which we are communicating should be able to seamlessly transmit from the transmitter to the receiver. So it should be able to accommodate diverse application. Ubiquitous coverage, symmetric coverage, or like uniform coverage in all direction is required. Then seamless indoor and outdoor operation. Transmission or performance in indoor environment should be equivalent to that in the outdoor operation. Device challenges will be your size of the device. So in order to increase the data rate, so like we have a limited size of mobile device, we cannot have a larger device which we can carry from one place to another. So size is a limitation. Then power, since you have limited power or the battery mounted on device has limitation. So power is a constraint here, which regulates your performance of the system. Then cost is also a constraint. When we talk about challenges on the device, then we have multiple antennas in silicon. Mounting antenna is another challenge because like when antennas are placed very close to each other, they interfere with each other. Then when you are using high frequency, then you will be using beamforming, directional transmission will be there. So there will be multiple challenges which are faced when we talk about antennas. Then multi-radio integration, the technology should be backward compatible with the existing technology. That is existing megahertz, the existing UHF band that we are using. So all multiple radio integration will be there. It should be able to support the UHF existing band, millimeter wave band, and if we move to the higher frequency, that is terahertz, then it should be able to accommodate all these bands. So, and then coexistence with the existing technology. So what are the technical backthroughs to achieve the connectivity goal? So network operating in millimeter wave and terahertz band with much so here, in order to achieve these connectivity goal, so network operating in millimeter and terahertz band with much wider spectrum resources. So when we move to higher frequency, we know that our spectrum available or the bandwidth available for communication will be higher. As your bandwidth increases, your data rate improves. Intelligent communication environment that enables a wireless propagation environment with active signal transmission and reception. So then you have environment. Here we mean intelligent environment because as we move to higher frequency, you will have directional transmission. So accordingly, your antennas will be accordingly mounted and will act. With active signal transmission and reception, large-scale network automation will be required. You'll have dynamic spectrum access will be there. You need to switch since as we move to higher frequency, the handoff will be very frequent. You'll be able to communicate to a shorter distances. So you'll have dynamic spectrum access will be required. Then he requires energy saving techniques because energy is when you talk about handheld devices, energy is a limited resource. Cell-free massive MIMO communication network. So like when we talk about simultaneously, we have different kind of moving devices that are accommodated. So we cannot, when we talk about high-speed vehicles or devices moving at high velocity, we cannot have small cell size. in that case, the battery will exhaust in the handoff itself. So here you need to accommodate a base station antenna, which can accommodate users with different requirement. So that's why we are like cell-free massive MIMO is another extension. Earlier we had this kind of cell division where you had hexagonal or like hexagonal because it's close to your cellular cell structure. So you have a base station accommodated with multiple antenna, which connected your users. So based on different techniques, you can have here we can like one-to-one connection can be there. If there is a beamforming, we are considering at the base station. So this was basically how your traditional cellular system used to operate. Now, if you have different size of the base station, which is or you are accommodating macro, micro, like heterogeneous cell structure is there. So with no specific base station, so in that case, you'll not have uniform divisions of cell as in your previous generation system. So cell-free massive MIMO is basically when you have no predefined cell structure is there. Your base station are mounted based on concentration of users in that specific area. So that's how the base station are mounted and will be connected to the devices. Because like you have more number of, when you have more number of users, then you need to reuse the frequency more frequently. So in that case, small cell sizes will be considered. So as you move from this basically improves your cell reuse factor. So here you have different base station mounted not symmetrically, which was there in the traditional cellular system. So based on user density, these base station are mounted here. Now there are different kind of wireless networks that are there. So which has specific call. So wireless Lan system is there, local area network. Then wireless MAN system is there, metropolitan area network. Wireless personal area network is there. So these are different kind of wireless area network which had different applications are there, and which supported with different IEEE standard. So the goal of Wireless Lan is provide internet access within a building or limited outdoor area. So that is the goal of wireless local area networks. It basically supported your cellular transmission. When we talk about WiMAX, so WiMAX is this is standard for WiMAX or wireless metropolitan area network. It provided access outside office and home network. Typically, regional access was provided by wireless metropolitan area network. Then we have wireless personal area network, which is based on, so these are the application of wireless personal area network. So corresponding applications are Bluetooth, Zigbee, and infrared. So through these features, it offered the connectivity. It transmits signal to shorter distances between devices in limited area, and the distance covered are typically in the range of 100 of meters. So communicate signal up to a very short distances. Then we talk about wide area network, high bandwidth networks are there. So provide access outside the range of wireless LAN and wireless MAN. So it provide even to longer distance communication is there. So provide access outside the range of, so whatever is not supported by wireless LAN and wireless MAN is supported by this LTE system. Now, what are the top wireless technology trends that are there? So these are the trends that we have. Wi-Fi, as we know, it accommodates or it facilitates transmission of data at very high rate. So it is very much part of the evolving wireless technology tree. Then 5G cellular is part of it. Cellular transmission will be there. Then the new income, then we'll have vehicle to everything. So that basically is part of, since we are looking for automation of vehicles. So vehicle to everything is a part of that. So long range wireless power. So now, like we have seen that wireless power transmission when we look at, so that Earlier, it was used to be connected through wire when we used to charge our mobile devices. Later on, you had a charging port and you had a surface which used to charge your mobile device. But still, you need to place your device on the surface in order to charge it. It cannot wirelessly transmit a device which is located far away from the charging point. So in future, what we are looking for is devices located distinct or far from a charging point, even that can be charged. So long range wireless power transfer is also a part of wireless technology trend. Low power wide area networks. So that will basically support high data rate. Millimeter wave wireless communication in order to accommodate more and more you'll be able to transmit more and more number of users here. Sorry. So here you'll be able to transmit more and more number of, because within the advancement in technology, you are requiring more data rate. So millimeter wave communication will accommodate that. Then software defined radio was basically targeted for in order to further utilize the existing spectrum that we had. So the existing spectrum, since it is finite spectrum, when we talk about the cellular spectrum or the spectrum that supports your wireless transmission, so that is a finite spectrum that we have. So software defined radio basically used to find the hole in the spectrum and will use that, was targeted to use that more efficiently in order to communicate. But it never took off because it is a expensive technology. So probably in future, with your MIMO system and your higher bandwidth transmission over millimeter wave, it may be feasible. Then we have wireless sensing. So sensor will be, so when we talk about multiple devices connecting to each other, so sensors basically fetch information at you can use sensors in order to fetch the information about multiple parameters. So that can be, these sensors can be multiple parameters when we talk about the condition of water and so inside the soil, or your number of vehicles that cross the road, or multiple functions that are there. So wireless sensing is basically connecting those sensors together. And hence wireless location tracking, because like with when we talk about millimeter wave also, we need to know in which direction you need to communicate. You need to know the location of the device. When we talk about vehicular to vehicular communication, location information if it is there. So like it's better to, so enhanced wireless location tracking is required as we move further in technology. When we talk about Wi-Fi, it will remain the primary high performance. So we are talking about each field individually. Wi-Fi, as we know, will always remain the primary high performance networking technology for homes and offices, right? It supports your high data rate communication. So there can be few new applications that might also be accommodated with the existing role that it is playing. So that could be radar system or a component or as a component in two-factor authentication system. So they might be few role that it may acquire over time. Then 5G cellular. So started, so existing, we have we talk about 5G and 6G system, but in practical, yeah, hello. Hello. Yeah. So when we talk about 5G and 6G system, we have successfully deployed 4G system. Now the deployment for 5G system has started, and it has started. It was started in 19 over different part of the world, and is expected to continue for 5 to 8 more years. May supplement Wi-Fi as a more cost-effective option for this 5G cellular may supplement for Wi-Fi as a more cost-effective option for high-speed data networking when you talk about large site, so such as airports, factories, etc. So like it may be more cost-effective when we talk about these scenarios, right? Because users want to continuously get connected to the internet. So maybe possible that this is more cost effective because we have now very cheap data plans are there as compared to getting these access over the airport or factories, Wi-Fi access over these locations. Its ultra reliable low latency feature has high potential in real-time critical control functions. So this is one feature of it. Ultra reliable. So like when we talk about 5G transmission, what it offers is it offers very high reliability as compared to the which is required in certain applications. When we talk about applications such as vehicular to vehicular communication or transmission drone based application, then that require ultra reliability and low latency. Small transmission time between the delay between the transmission and reception, and data communicate, because when you communicate the control instruction, you require that it is reliably communicated. So it has high potential. 5G cellular communication has high potential in real-time critical control function and communications such as these. Then we'll talk about vehicular to everything communication. So when you so this is one more area that is wireless technology trend that is explored. Vehicular to everything is, it enables basically conventional and self-driving cars to communicate with each other and with the road infrastructure. So over future, we are looking for driverless cars which can move themselves from one point to another. That will basically offer more safety. It will provide, V2X will provide increased safety, navigation support, driver information, and fuel saving. Right. So when the cars, their speed, because each lane or each vehicle has certain speed limit is there. So when it is centrally controlled, then in that case, you'll be able to optimize the transmission velocity. It will be independent of who is driving the car, right? So you'll be able to accommodate the traffic in a better way when you have vehicular to V2X communication is there. So vehicles will be properly over the road. They will be properly mapped and will be drive so that the fuel saving will be there. To make V2X technology are dedicated for short range communication. So when we talk about V2X technology, there are two standards that are continuously being explored for V2X communication. One is short range, dedicated short range communication standard, and cellular vehicular to everything CV2X spectrum. So both the spectrum are simultaneously explored in order to support V2X communication. Then we also talked about long range wireless power transfer. Existing wireless transfer schemes that we know about only supports, like you can place a mobile over wirelessly over a charging some surface which is supported by a charging port. So that is what we are able to achieve when we talk about wireless transfer till now. So in future, we are looking for application where the device is located far from the charging point and still it can be charged. The new technology can charge devices at range up to 1 meter or over a table or desk surface, any surface we are able to charge the device. Long range wireless power could eliminate power cables from desktop devices. So that is the target here when we talk about long range wireless power transfer. Low power wide area network. So you provides power efficient and low bandwidth. There are certain technologies that is there for wireless power transfer. Simultaneous wireless power transfer is there. Then like multiple wireless RF-based power transmission is there. for long-range wireless power communication. Then we have low-power wide area networks. So it basically implies provide power efficient and low bandwidth connectivity for Internet of Things application for long battery life. So it supports or it accommodates long battery life, enables small low-cost battery power devices such as sensors and trackers. So these are the features of this. Then we talk about wireless sensing. So it can be used in application ranging from medical diagnostic to smart homes. Right. So the application of wireless sensing can be very wide. It basically can be mounted in the body, and you can determine the different parameters inside the, or you can do the medical examination in the body, or it can be mounted on any surface, or like you can have wide application of wireless sensing. It is even used like on road. You can mount in order to check the velocity, or like multiple factors can be monitored using sensing devices. You can use wireless signal for sensing and applications such as indoor radar system for robots and drones or virtual assistants too. So these are certain applications of wireless sensors. So wireless signal can be used for sensing in applications such as indoor radar system, right, for robots and drones, or virtual assistant to improve performance when multiple people are speaking in the same room. So like it's localized. Sensors are basically can be mounted, can be made more localized, and it can accordingly improve the performance. And hence wireless location tracking. So the this is one of the technology trend where when we talk about directional transmission, it's always better to know the exact location of the device. So in order to reliably communicate the signal. So location sensing integrated with a core wireless network could provide several benefits such as lower hardware cost and power consumption. So you are able to communicate more efficiently when you know the location of the device, improve precision and performance. So these are the advantages that are offered by wireless location training. But next we'll talk about millimeter wave wireless communication. So millimeter wave, as we know of, can support wide bandwidth, so improves your data rate here. So it operates in the range of 30 to 300 gigahertz. So that is basically not entire band is your millimeter wave band. So here, in millimeter wave range, the bandwidth is in the range of. So this is the wavelength in range in millimeter wave. It be used for wireless systems such as Wi-Fi, 5G for short range, high bandwidth communication. We'll see millimeter wave in more detail. So why we move to millimeter wave, or you can say any high frequency wave, even terahertz wave for that matter. But like for now, in the in 5G technology, we are specifically looking for millimeter wave. As we move to the higher 6G or further generation, will be even moving to higher band, higher frequencies. So by millimeter wave, it can accommodate the growing need of subscriber. It can accommodate more and more number of subscribers simultaneously. It provides higher data rate. With the soaring number of smartphone and tablet, people browsing web, stream video, and share photos on the go, the data moving over wireless media has increased. Mobile traffic worldwide is doubling every year. So the techniques devised to enhance the capacity of 4G LTE cellular network, like the existing system, MIMO, smaller cell. So in 4G LTE cellular system, these were the technology that were used in order to improve the data rate. Like MIMO system was used, more antenna, higher data rate. Smaller cell were used to reuse the same set of frequency more frequently. Smarter coordination between devices, so better management scheme were used in order to improve your or accommodate or increase the data rate in 4G system. etc. So these advancement in technology in 4G system are not sufficient to meet the growing demand for data. So that's why we move to the higher frequency band. So how it communicates, or like what kind of communication. So this is a rough like an overview of how it operates. The different links are shown here. So this is your serving base station where multiple antennas, directional antennas are mounted. So it can communicate directly to your mobile device. So this is kind of line of sight communication between the serving base station, which is communicating millimeter wave signal. So LOS communication with the user equipment, or can communicate with the help of relay to the mobile device. So this is when you are communicating over longer distance, then you can even use the relay for communication. Then you can have millimeter wave, although it has higher losses, but like it's not true that it does not support non-line of sight communication completely. It supports to some extent or to some distance, and LOS communication is even supported by millimeter wave. So it also supports this thing. However, the attenuations will be there. It can support millimeter wave backhaul link, and other base station in the vicinity will be acting as interference for any of the transmission that is happening. So why we switch to millimeter, or when we talk about 5G system, why we talk about the millimeter wave communication? The reason is the current cellular technology has frequency range in the range of 300 megahertz to 3 gigahertz, right? And whereas the future millimeter wave technology, or that we are targeting for, has the frequency range in the range of 10 gigahertz to 300 gigahertz. So the available spectrum here is 700 megahertz. And whereas if you see, this is the growth in the spectrum, or for transmitting the data. So here the available spectrum, instead of 700 megahertz, when you talk about millimeter wave technology, is 100 gigahertz. Maximum data channel bandwidth. So per channel, the bandwidth will be 100 megahertz. So as we know that bandwidth is directly proportional to your data rate, right? So as your bandwidth increases, your rate at which you communicate the data will also improve. So here it offered channel bandwidth, maximum data channel bandwidth of 100 megahertz, whereas when you look at millimeter wave communication, it offered up to 1 gigahertz. So data rate is proportional to your bandwidth. So here earlier in the existing system, data rate was 13 megabit per second, whereas if you talk about future millimeter wave technology, so in that case, data rate that it can accommodate is 1 gigabit per second. Millimeter wave will also have application in vehicular communication. That is, if you talk about millimeter wave in vehicular communication, there will be certain set of communication which is supported by cellular transmission, whereas a certain portion of because when you talk about vehicular to vehicular communication, there are multiple parameters that need to be monitored. It will be, you have sensor mounted on the vehicle, so that information need to be fetched. Then location information need to be tracked. So there are multiple links which are operating simultaneously. Then there are cameras on the car, which when you for processing that data, you require high data rate. Your vehicle, or like for that transmission, high data rate need to be supported there. So here it will be using both cellular band as well as millimeter wave band when we talk about vehicular communication. So the metal of vehicles may act as a reflector for millimeter wave signal, which result in strong interference. So when we talk about high frequency, then it because your vehicles are made up of metal, so it will pose strong interference when you communicate the signal over millimeter wave. Dynamic topology and changing radio conditions, devices mounted on vehicle will be moving at higher speed, so you have challenging radio condition are there when you talk about millimeter wave transmission over for vehicular communication. However, it offers high data rate requirement is offered here. The data rate, as we have already seen, is in the range of 1 gigabit per second for high quality uncompressed images. For local view, vehicles rely on many high resolution cameras. So for nearby in vicinity surroundings, when you observe it, because there will be multiple parameters which need to be observed in order to make the car driverless. So which also requires deployment of cameras. So vehicles rely on many high resolution cameras and sensors. So LiDAR for 3D mapping for accurate target detection and velocity estimation. Data rate required here is 10 to 100 megabit per second. So this is for the local view, it relies on these things. Whereas for wider view, autonomous vehicle will need to communicate with each other. So you'll have vehicle need to see its own surrounding. Also, it need to communicate with the nearby vehicle. So if there is a brake or what is the speed and these parameters, if need that also need to be communicated. So you'll have vehicle to vehicle communication and the surrounding infrastructure. If there is a wall or like, so these also how the way is there, in which direction it will be moving. So surrounding, it also need to communicate to the surrounding. Cell radius of 1 millimeter transceiver. So this is the property of millimeter wave. When we talk about, so when we say millimeter wave has high attenuation, but still even with high attenuation, if you see, it can communicate up to a distance of 200 meters. Right? So it is observed that with millimeter wave, you can have cell radius of 200 meter. Also, when you talk about cellular communication and when you talk about femtocells and all that, in order to increase the GU spectrum, that supports a cell radius of around 100 meters. So this is not, which is worst, right? So here, millimeter wave transceiver can communicate signal reliably up to this distance, right? So which is comparable to UHF cells, ultra high frequency cells. So these are the different scenarios, vehicle scenarios that we have. Vehicle need to communicate to different surrounding. The surrounding can be vehicle to infrastructure, how the infrastructure is located around it. Vehicle to network communication will be there. So vehicle to network is there. Vehicle to road signs will be there. Stop, on, all these things the vehicle need to know whether it need to drive or not. Vehicle to satellite in order to get the location information. Vehicle to drone. So probably to connect the multiple vehicle together or for the location information. Vehicle to sensor. So sensor, it can control like how is the ground coverage, or like back curve when you are moving car, taking back, moving it reverse, right? So in that case, the sensors are there that can work. Vehicle to people communication. So that is basically when people are crossing the road, then you also need to see that. So that is also there. That is also a part of vehicular communication. Vehicle to roadside infrastructure with roadside unit. So that also supports your part of vehicular scenario. All these things communicate different kind of information. Also, like vehicular communication is not very simple. You have multiple it need to communicate to multiple surrounding in order to so driverless communication require all these things. Now, this basically talks about standardization when we talk about vehicular communication. So two of the standards are widely explored. One of them is 802.11p. So amendment of this standard for Wi-Fi. So this is basically a standard. 802.11 is basically a standard for Wi-Fi. So to this standard, vehicular transmission, there are few amendments that are made in order to complete vehicular communication. So this 802.11 add access to vehicular environments. addresses vehicle speed of more than 100 km per hour because the environment will be frequently changing. So the standard support this through the formation of vehicular ad hoc network. Data rate that it can support is 6 megabit per second to 27 megabit per second. And so that is one standard. When we talk about there's another standard, will target future vehicular service requirement through modulation scheme. So here, what is the parameter that are changed in order to communicate the signal are modulation scheme, the introduction of mid-ambers, improved channel estimation in fast-fading conditions. So this gives you an overview of how in comparison to how the two these standards are compared when we talk about the different parameters. So OFDM subcarrier spacing in this standard is this 156.25. When you talk about 802.11 BD, so the carrier spacing is this. Then you have forward error correction coding. So FEC coding is BCC in case of the standard and LDPC in case of IEEE 802.11 BD. Channel estimation is done through preamble, whereas it's done through midamble in case of this. Modulation scheme that is employed in case of the standard that is based on Wi-Fi is 64 QN, whereas it can accommodate up to 256 QN. Then channel estimation in the range of 10 megahertz. Channel estimation 10 megahertz, 120 megahertz channel. Then here this retransmissions are not there. Here this accommodate or this allows up to 3 retransmission if the channel is not signal is not reliably communicated. You have fast VSS transmission is not supported in this, whereas transition is supported in this. Error correction, part of data packet is error corrected, dedicated packet sent separately. So in order to, for error correction, the packet loss is separated separately. Both standards will support operations at millimeter wave frequency up to 17 gigahertz, where the large available bandwidth can theoretically enable connections with data rate in the order of multiple gigabit per second. So now when we talk about, since you do not have traditional channel model fitting the millimeter wave communication, because the chances that there is a LOS, like if there is no LOS path, so in that case, the chances that signal will be reliably received reduces. So most of the time when you communicate signal over millimeter wave, you target for LOS transmission, or like if LOS link exists, then communication will be best, or you can communicate up to a relatively longer distance. So these are different channel modeling techniques which are used in millimeter wave communication. It will, since attenuations are more, it will perform better if these channel modeling techniques are used here. So ray-based modeling model directional transmission in millimeter wave frequency within link formation framework on top of ray-based modulator. So here, like exact structure of the building, you try to trace it using ray tracing techniques. So what are the path laws when you communicate a signal from point A to point B in that surrounding? You can determine it from the model itself. So specification, transmission frequency here is 28 gigahertz. Directional antenna are used. All cars are equipped with 4 antenna, one on each corner of front. So all bumpers are mounted with one antenna. Antenna height is 0.35 meter. Every antenna pattern is approximated by a Gaussian shape. So it's considered that antenna pattern is Gaussian shape, has Gaussian shape. So these are the specification of this model. Simulation mechanism that is there is collect channel state information. So channel state information in terms of angle of arrival, angle of departure, time of arrival, received power. So these are the these will give you channel state information from all transmitter to all receivers. will be required in this specific model. It's a tedious model in order to it's very, it's an accurate model of the surrounding, but knowing this model is very tedious. Millimeter wave communication, millimeter wave pass through drive well. So these are the surroundings through which, like we say that millimeter wave cannot penetrate across the surfaces because they are high frequency signal, or their wavelength is very, very small. But there are certain surfaces through which the millimeter wave can propagate. So one of them is dry well and clear glass without losing much energy, but are almost completely blocked by brick. So when you have concentrated material is there, so in that case, the signal will be completely blocked. The material can be brick, concrete, and heavily tinted glass. Users might get some reception in those, but operators need to install repeaters or wireless access point. So millimeter wave communication, as we know, is a short distance communication. So when you want to extend the range, then you can use the repeaters here. Here, we know that you need to have, so it is a short, high attenuation are there. You cannot transmit very high power at the transmitter side because the battery will drain if it is a wireless device. So what is done here is multiple antennas can be deployed on the device so that it can transmit data at a higher rate. So what is like the first, we know that millimeter wave, basic transmission of millimeter wave over a wireless medium was first done in 80s by Indian scientists. So later on, so that was the first transmission that was done using a bulky motorized horn antenna, which is now replaced by an array of rectangular metal plates called patch antennas, right? Because we want to accommodate whatever the antenna on your wireless device. So now this is replaced by an array of rectangular metal patch antennas. The antenna size is at least half the wavelength, that is about, so in millimeter wave, wavelength will be very small. So 1 centimeter for 28 gigahertz will be there, and each patch antenna could be just 5 millimeter across, right? So this will be the dimension of millimeter antenna that will be needed, because these antennas are mounted on the chip. For cellular transmission, a single patch antenna would not be sufficient as gain decreases as antenna size shrinks. So when you talk about cellular transmission, so when having a single patch antenna, will not be, so energy will not be sufficient, would not be sufficient as gain decreases as antenna size shrinks, because your gain transmitted, antenna gain will reduce as the size of the antenna reduces. Therefore, an array of antennas can be arranged in a grid pattern. So this is what is done when you move to higher frequency, because the antenna size is very small. So you use a grid pattern of antennas to magnify their collective energy without increasing the transmission power. So using a grid of antenna basically increases your transmit energy. So this is how millimeter wave behaves in environmental condition. So in case of, so here it shows attenuation due to molecular absorption. So if you see the plot, it varies, it is different at different frequencies. So at certain frequency, attenuation is small, whereas like even at higher frequency, attenuation is small as compared to 60 gigahertz and 120 gigahertz. So it varies. So this shows with molecular absorption how the attenuation varies. With rainfall, how the attenuation when you transmit the signal over millimeter wave varies, is shown in this figure. So in order to guarantee coverage, millimeter wave devices need to perform beamforming. But if you are transmitting signal in all directions, the chances that it will be able to communicate signal reliably will be very small. So what you can do is you can perform directional transmission through beamforming to concentrate energies, because through beamforming you'll be able to communicate to longer distances. So millimeter wave devices need to perform beamforming to concentrate energies small angular space. Directional communication not established due to misalignment between the beams of the transmitter and receiver. So like when you are communicating through directional antennas, what happens is you need to align the receive antenna in order to receive the signal. The receiver antenna should be in the same direction. So that alignment is required here. So directional communication not established due to misalignment between the beams of the transmitter and receiver is addressed using beam training. Right? That is an operation in which transmitter and receiver find a beam pointing to each other. So you need to align the beam at the transmitter and receiver in order to communicate the data. The alignment process complicates the link establishment but substantially reduces multi-user interference. So it is a complement. This alignment process, aligning the two beam, is actually a tedious process. But the advantage of this is that because of alignment, it will not affect the neighbors. So multi-user interference will not be there. High penetration loss due to because of directional transmission, this interference, multi-user interference will not be there. High penetration loss due to obstacle. So since you are transmitting or communicating over high frequency, the loss will be high. Addressed using alternative directed millimeter wave channels that are not blocked, which may be provided by reflector and or intermediate relay node. Then beam management, which includes initial beam alignment, monitoring, tracking, recovering from beam failure is crucial. So this is beam management. You need to have perfect alignment between transmitter and receiver in order to extract the information. In a mobile network, the transmitter and receiver would connect with each other by sweeping their beams rapidly. So this is one mechanism of beam alignment. So transmitter receiver that are connected to each other, which need to communicate to each other, sweep their beam rapidly so that they are able to align with each other until they found the path with the strongest signal. This is one of the beam alignment techniques. Here, this table basically states the different spectrum band that are used in the 5G and 6G system. So in the 5G system, we have seen this is your basically a millimeter wave, 30 to this is also millimeter wave. So we'll be individually talking about, then this is terahertz band, this is also terahertz band. So each band has its own specific feature. This is the one band which is currently used for cellular communication, that is less than 3 gigahertz. The wavelength here that is supported is 100 to 10 centimeter. In 3 to 30 gigahertz, 10 to 1 centimeter is the wavelength. These are different bands on the spectrum, right? Millimeter wave starts from 10 gigahertz. So for this specific band, these are the wavelengths that are mentioned here. There are certain specific features about these frequencies. The features are mentioned here. The communication happens when you talk about sub-gigahertz band. So the communication established through line of sight, reflection, diffraction, scattering, and penetration. So these are the mechanisms at low frequency. As we move to higher frequency, line of sight will be there. The transmitter and receiver should be in vicinity. Reflection, diffraction, and scattering. These phenomena will be there through which communication happens. There will not be communication through penetration because the signal loses. It is lost at high frequency because of penetration. Then when you talk about 30 to 300 gigahertz, the communication will be established through line of sight transmission and reflection, which you specifically need a LOS communication as there is an increase in or as you move towards the higher frequency. This indicates basically what are the dominant attenuation effects that are there when we talk about higher frequency band. Free space loss will be there in this band. Free space loss, transmission loss through materials high at upper band. So this talks about the losses for different frequency band. So atmosphere will be lost and different factors will be lost as you move towards the higher frequency band. These are the supported link distance. To this distance, or you can say this is the cell radius to which the signal can be communicated. So the radius is 10 kilometer for sub gigahertz band, 1000 meter for this band, 100 meter. So it reduces with the increase in the frequency. Supported link distances reduces with the increase in frequency. Transmit power here is a limiting factor. So here different regularization standardization has been done. Here technology is evolving. Approximate system bandwidth here is up to 100 megahertz, whereas here, so this is the, as we know that data rate increases with the increase in bandwidth. So as you move towards higher frequency, higher bandwidth will be available and you'll be able to support data, or you'll be able to transmit data at very high rate. So these are the supported bandwidth with increase in frequency that is mentioned. So in 5G and 6G system, these are the key performance indicator. So one of them are the parameters that describes your system capacity. So system capacity is described in terms of these parameters. One is peak data rate, that is mentioned in terms of gigabit per second. So when you talk about 5G system, it supports data rate up to 20 gigabit per second, whereas what we are targeting for in 6G system is data rate up to 1000 gigabit per second. Here, experience data rate, fine. So this is peak data rate in the best condition that is targeted for. This is what we actually get. So that is 0.1 gigabit per second, whereas in 6G system, it is 10 times better than this. Fine. Peak spectral efficiency here is 30. So this is the spectral efficiency, how efficiently are able to use the spectrum allotted bandwidth. So spectral efficiency will be 30, whereas it is 60 here. Experience, so this is peak. The experience is 0.3 and 3. Maximum channel bandwidth that is assigned in 5G system is 1 and is 100 gigahertz in case of, so bandwidth increases as you move towards the higher frequency. Area traffic capacity, so it's like when we talk about, so basically what we are doing is we are comparing millimeter wave transmission and terahertz band transmission over terahertz band, right? 5G will also include your existing cellular band. So like what are the changes we are looking at? All that changes only. So like 5G system, we are here we are basically looking at millimeter wave, how it will improve the technology. 6G terahertz band, teraband, how it will be improving the technology that we are looking at. So when you employ the terahertz band, this will be the bandwidth. When you employ millimeter wave, then this is the bandwidth. Area traffic capacity is megabit per second per meter square. So it is 10 and 1000 here. Connection density, like how many devices will be accommodated per kilometer square, is 10 to the power 6 devices will be accommodated in 5G system, and it's targeted to be that can be accommodated in 5. So this is the maximum capacity. 10 to the power 7 that we are targeting for in the 6G system. Right? We look for improvement in all the parameters. When we move from one technology or with the growth, you'll have improvement in all the parameters will be there. End-to-end latency or delay in, you'll have latency will be 1 here and is 0.1 we are targeting for. Delay jitter, here we are looking for, it's not applicable here. Here it is 10 to the power minus 3. System management, when we talk about system, how efficiently your energy that is communicated through the device, or you can say it will monitor basically health of your battery. So energy efficiency here will be 60, it's considered to be one terabit per joule. Reliability here, 5G system is still evolving, right? Reliability here, packet error rate is, so this is the reliability in 5G system. What we are targeting for is this. Mobility is 500 km per hour. So this is very rare application where you have velocity is 1000 km per hour. Even 500 is very high, but there are certain examples where you have velocity up to 300 km per hour. Like in Japan, there are bullet trains and these things are there that communicate or that moves with very high velocity. Use cases best served by 6G system. So it gives an overview of the what are the targeted application of 6G system. So autonomous vehicle, which we have already, vehicular to vehicular communication that we have seen, self-driving will be what we are looking at as we move from 5G to 6G system. Then we are looking for space connectivity that is existing, will be an extension of the present thing. Space connectivity also includes, with the evolvement of technology, it also includes unmanned aerial vehicle. So like even a possibility of Wi-Fi connection over space, right? So the devices in space will also be connected. Smart infrastructure. Then this is a new feature, holographic teleportation. We know that in 5G or now the users, what they are looking for, that even social networking is online, interacting with people is online, then shopping is online. There are many things that has video conferences there. So many things that has moved online. So because of all, so this holographic teleportation basically will provide you even more real experience where you have 3D image of the person or object will be there next to you. So it will provide you even more better realization of the thing. So that is a part of 6G system. Then precision agriculture will be one of the cases or use cases will be there. Industrial automation, right? Then remote healthcare, now your smartwatch can measure your BP, heart rate, many parameters can be measured through your smartwatch. So remote healthcare is basically connecting hospital, ambulance, since your health monitor or health information is available on the smartwatch itself. So if there is any requirement specific to that comes up, so it will remotely connect you to the support, right? So that is your remote healthcare. Smart environment, so consumption of different things, you have smart sensors are there, which will monitor your consumption of different parameters here. What is the, or you can see that what is the heat changes over the, there many things can be measured here. So smart environment, which also include your smart city. So will be one of the use case of smart evolved use cases of 6G system. This is basically base station mounted with multiple antenna. All these applications cannot be supported without the assistance of multiple antennas, which is required for higher data rate. Also for coverage extension also, because when you talk about millimeter wave, it will not be feasible to communicate longer distance or with higher power without the support of MIMO system. Right? So these are the different applications which we are looking for in 6G system. Now, these are the technology which enables these applications. So here, terahertz band communication, when we talk about 6G system, so we need to move to higher band. So these basically mentions open problems that are there. So antennas and all these things are not yet developed when we talk about terahertz band. Key performance indicator is basically system capacity. It improves basically these terahertz band basically improves your system capacity. Communicate wider bandwidth will be available. Data will be communicated over higher rate. So open problems are fabrication and testing of antenna arrays. It will not be an easier task to communicate signal over this band. Real-time control application in receivers. Communication protocol for coordination between transmission. So these are certain open problems when we talk about terahertz band, which you might be partially familiar about. Then intelligent communication environment. So you have it will be controlled through different sensors. You have or information about. So here, open problem will be trade-off between dimension and energy consumption, compatibility with the existing. So these are key enabling technologies which are there. Network automation, pervasive artificial intelligence. So this connects basically multiple sensors together. Then your antennas, reconfigurable transceiver front end, their design need to be. So these are certain 6G enabling technologies are there. Then ambient backstable communication. It is basically to use energy more efficiently, right? So this is basically because energy is a limited resource. So this technology is basically to use energy more efficiently. Then Internet of Space things. So you have drones and other things are there. So connecting them together will be part of 6G system. Then cell-free massive MIMO we have already talked of. Internet of Nano Things. When we talk about smart cities, smart homes, so in that case, many sensors are there. These sensors need to be mutually connected to each other. So that is basically nano things connected through internet. Sensors, multiple sensors connected through internet. The Internet of bio-nano things. So will be there. Then quantum communication. So these are the key enabling technology which will be present in your 6G system. So this is one of the references. Others I have mentioned within the slides itself. So this is one more reference that I have followed. Thank you. If you have any questions, you can.
So the question is, as you just discussed, that the link distance decreases with increase in frequency from millimeter to terahertz. How it is going to affect the coverage, and what measures need to be taken for that?
So like basically, as we move to higher frequency, the losses attenuation will be very high. So then what we can do is we will be using precise transmission from user to base station. Multiple antennas will be used. So directional transmission will be there. Energy that is transmitted at the source will be communicated in a like very precisely to the destination. So it can move to a longer distance. Energy is limited resource. So like if we broadcast it in all directions, then it will be lost and it will not be able to reach the destination. So we'll transmit it very precisely from the transmitter. So many directional antennas will be needed here. So as we move higher in frequency, you'll have directional transmission will be there. Then will be connecting through even the software part need to be very strong. You have precise orientation between the transmitter and receiver is required because the beam that is communicated should be precisely transmitter and receiver. The beam should be in the same direction. Then only the connection will be established. Okay?
Thank you.
So,
thank you. Yes.
Yeah.
Okay, madam, that Dr. Sunandita Debnath has one
Ye-
question. Please, you can ask.
Yeah, yeah. Am I audible?
Yeah.
Yes, you are audible.
Yeah. As ma'am, you have discussed that with the increase of frequency, as we are moving to terahertz zone, the wavelength will be decreasing, which is obvious. So we need a much smaller number of smaller size of cellular cells. So the cell size will be reduced, and so the number of the smaller transmitter, that is BTS, will be increased, which I understand like from your discussion.
Mhm. Yeah, as you move higher in frequency, automatically attenuation will increase. Because of that, the distance to which you can communicate will reduce. So it will have limited application. It cannot support all kind of application. Like you're using, if you're pushing data over short distances, right? So in that case, for specific part of the technology or application, it can be used. Like it cannot transmit a signal to a longer distance, but we have applications where like we are doing live streaming or the entire office is watching the same video. In that case, the distances are small and we can use these higher frequency there. So it has limited applications out there.
Okay, and obviously the attenuation will be very high because the wavelength will be almost in the same dimension as the water content in the atmosphere. The
Yes.
dimension, yeah,
Yeah.
yeah, yeah.
So antennas, they need to be very precisely designed. So like how the thing evolves, it will be a part of future.
Okay, okay. Thank you, ma'am.